This is a quick video on osmosis to help you fill in page 9 in your lecture notes. In the video, I'll explain the concepts related to osmosis, which I won't be covering in class. We'll follow up in class with calculations of osmotic pressure. So what is osmosis? Osmosis is, as it says in the description there, the passage of water through small pores and a thing called a semi-permeable membrane. And the water is always going to be moving from a region of low solute concentration to a region of high solute concentration. Now, in some of your biology classes, your biology professor might correctly state this slightly differently. They might say the water is moving from an area of high water concentration to an area of low water concentration, which is also correct. In a solution with a high solute concentration, the water concentration will be lower. So in the example on the right, you can see that we have pure solvent actually on the left, and we've got a solution with some solute particles on the right. And you can see that the concentration of solute is higher on the right, the concentration of solvent water on the right is lower, and the reverse is true on the left. One thing to keep in mind with regard to osmosis is it's always the water molecules that are moving across the semi-permeable membrane, not the solute particles. The solute particles, it turns out, are, as you'll find out in a minute, they're too large to pass through the tiny little pores. Only water molecules can pass through the pores. So to understand osmosis, we first have to understand this semi-permeable membrane. As I said just a little while ago, it has pores in it, or little openings or holes, through which only water molecules can pass because the pores are very small. And the solute particles have lots of water molecules stuck onto them, as you can see over on the right. Those purple solute particles with their water molecules are too large to pass through the pores, and therefore the only things that can go through those pores are the water molecules. Let's see. The two different behaviors of water, therefore, in a solution are these. You have two different kinds of water molecules. Number one, water molecules might be free water molecules. They move independently of solute. They're not stuck on a solute particle or attracted to one. And then you have what are called solvating water molecules. And those are the water molecules that are physically attached by intermolecular forces to a solute particle. So those are our two different kinds of water molecules. We want to know then, how do those two different types of water molecules behave differently? First of all, the water molecules that are free can move both directions across the semi-permeable membrane. It's not just a net movement from the low solute side to the high solute side, in this case from left to right. It's not only in that direction they can move. Water molecules can move back from the right to the left as well. Keep in mind, the water molecules move across the semi-permeable membrane in both directions. And this should make you wonder, then why does water tend to have a net movement to the right? So we'll answer that question in a little bit. Keep in mind, water moves in both directions across the semi-permeable membrane. But how about those solvating water molecules? The problem with them is that they're surrounding solute particles, and like we said, they cause the solute particles with their hydration shells to be too large to pass through the pores. So let's summarize. Why is it, in fact, that osmosis occurs? Why is there a net overall tendency for water to move from the left to the right in this diagram, from the low solute to the high solute side, from the high water concentration to the low water concentration side? Well, the reason is just probability. If we look at the left-hand side, we can see that the probability of a water molecule bumping into the membrane, and therefore the probability of a water molecule bumping into a spot where there's a pore, is much, much higher than the probability of a molecule of water on the right bumping into the semi-permeable membrane and passing through a pore. It's just probabilities. On the left, the probability is higher. On the right, the probability is lower. So finally in the video, let's then explain how this process of osmosis gives rise to the thing we call osmotic pressure. And you can see in our diagram here that we've got a blue solution separated from a green solution by a semi-permeable membrane. And the blue solution is pure solvent. In other words, it's a solution that has a high concentration of water. In the green solution, you've got in the green part of the tube there is a solution, which must therefore contain a solute if it's a solution. So it has a lower water concentration, a higher solute concentration. And therefore you can assume, based on the previous diagram, that water is going to have a tendency to move from the blue side to the green side, from the pure solvent to the solution. And in the middle of the three diagrams, you can see that the water has proceeded to move through the membrane and is causing the height of the liquid in the rightmost part of the tube to be higher and the height of the liquid in the leftmost part of the tube to be lower, because water has moved through the membrane and is only going to be stopped in its movement through the membrane. It won't just keep moving. It'll only be stopped once the solution on the right is too heavy and gravity stops the movement of water. So there'll be a final height of the solution on the right and a final lower height of the solution on the left. Okay, to answer the question, what is osmotic pressure? It's the pressure that we would have needed to have applied in order to keep osmosis from occurring. So if we apply pressure to the high solute side, then it will cause the net movement of water molecules to be equal back and forth across the membrane, and we can keep those two levels at the same value. Keep in mind that when we have our two solutions that are separated by the semi-permeable membrane, one of them might be pure solvent and the other might be a solution, but they both might also be solutions. One of the two liquids might be a low concentration solution and the other might be a high concentration solution. And the business with osmotic pressure is the solution that has the higher solute concentration is the one with the higher osmotic pressure. And you can see that we would have to apply a pressure to the green solution. That's the one that has the higher osmotic pressure. We'd have to apply a pressure to the green solution to push it back down and keep those two levels equal. In other words, if we summarize everything as the solute concentration increases, osmotic pressure increases. That's the end of the video. Now you understand, hopefully, a bit about osmosis, and we can get on in class with the process of doing calculations of osmotic pressure.